Hi, today we're going to look at the ROP Emporium Write For challenge, and the description says, our first foray into proper gadget use, a useful function is still present but we'll need to write a string into memory somehow. So a little bit more information. In the previous example we had bincat and flag.txt. They were existing in memory as strings and we needed to join them together. This time we don't have the strings in memory at all, so although there are other ways around this problem, such as resolving dynamically loaded libraries and using the strings present in those, we're going to stick to the challenge goal here, and we want to write a string into memory so that we can cat out this flag.txt. There's a little bit more description here which I'm going to go through. Things have been arranged differently for this challenge. Printing logic has been moved into a separate library in an attempt to mitigate the alternative solution. That's fine. Stack smash also takes place in a function within that library, but don't worry, this will have no effect on your ROP chain. And there is a PLT entry named print file, which exists, and we simply need to call it with the file that we want to read, flag.txt, as the first argument. So I'm not going to read through all this. Essentially it's telling us we need to look for ROP gadgets to move, so we need to basically write data to memory here, so we're not going to just be looking at like pop gadgets as we have done in the previous exercises. The most important thing to consider is where we're going to write our memory. So flag.txt, saying we can use rabin2 or readelf to check out the different sections and the permissions and see how much space it will have. So we need to not just look at the size of particular sections, but what data is already in there and whether overwriting that data would cause problems later on down the line. And once we've figured out how to write the string to memory and where to write it, we want to go ahead and call print file with the location of the string in memory as the only argument. It also says here you consider wrapping your gadgets in a little helper function. So if I remember, I'll not do that later, but I'll just describe what it's talking about and what we could do in that example. So let's jump straight into the 32-bit binary. And if we run checksec, we can see, as usual, no execute is enabled. We don't have any other stack protections there worth taking into consideration. We can run rabin2-z and have a look at the strings. Okay, not much. We have this string non-existent here in the RO data section, and we can have a look at the functions. And we have the pwnme function and the print file function that was mentioned previously. Let's also open up radar2, and if we run AA to analyze all sections, we can do IS to have a look at the sections here. And this is what was mentioned in the challenge description, that we need to look at the different sections, as we can see here, and the size of the sections, and then obviously what's actually in the sections. Once we've found somewhere suitable that we can write the memory, that we can write the data to, we'll take a copy of the address. So looking at this, we know that we need to write 8 bytes for flag.txt. There's 8 bytes here in the .data section. There are also we have 8 bytes in the plt.got section, but this is more likely to overwriting. That's more likely to cause issues. So we'll just bear that in mind. We can have a look at the imports. So we have the pwnme and print file. We can have a look at the full list of functions. Pwnme, we have this useful function as well. We have print file. Let's take a look at the useful function. We can do s and pass in the function name, and then we can do pdf and have a look at the function. So the useful function calls print file after pushing the string non-existent to the stack. So our goal is going to be to replace this with the address of the flag.txt once we write it to memory. So let's close this down. We'll get ready to have a look at this in GDB. I'm just going to jump over first of all to Ghidra. And you can see here we're in the main function. It simply calls pwnme, and that's all, but we have the useful function in here, the non-existent string, the call to print file. So yeah, you can see here the pseudocode print file is being called with non-existent as a string, and we want to put flag.txt in here. If we have a look at the sections here, so we have the .data section we were looking at, which had 8 bytes free, and note that there's nothing actually in here at the moment. They're empty bytes that we can use, whereas if we looked at the got.plt section, which had 8 bytes as well, you can see that there's already data in here. So it can just be a case of going through and having a look to see if any sections have any space that we can write to. For this example, it looks like we'll probably use the .data section, but there may be other solutions in here if you want to explore trying to write to other addresses. Okay, let's go back to our Linux system and have a look at the GDB. We'll try and find the EIP offset. So as in the previous examples, we boot up GDB-pwndbg, and just to change things up a little bit, I showed in one of the first videos, I think, the difference between GDB-pwndbg and pwndbg in terms of searching for patterns, and you know, pwd certainly has a better solution for that. But let's have a look at GDB-jeff. This is just another plugin for the GDB debugger, and if we open this up, we can do pattern create 100, and that creates a cyclic pattern similar to the other two plugins that we've used. We can then run the application and paste that in. It crashes. You can see here it's slightly different layout, different color scheme and things like that, and we can see that we've overwritten the EIP with LAAAA. So let's try pattern search. Okay, so pattern search, and then we need to put in the pattern, so LAAA. There we go, and it tells us then whether the little endian and the big endian offsets, and states that the little endian is more likely, which it actually says 41 there. That's interesting. Let's go back to pwndbg. Cyclic 100. Let's create a pattern. Run it, and let's do cyclic -l LAAA. Okay, 44 here. Okay, so the big endian search was actually correct there. Okay. That's interesting. Anyway, I thought I'd check that out. Let's stick with pwndbg for now. So we now have the offset. We know that we're going to write 44 bytes to the buffer before we get to our return address. I'm going to just open up a text editor, and we'll use this to try and get an idea what structure we want our payload to be in. Okay, if we have a look in pwndbg, we can disassemble the useful function, and if we have a look here, we have useful function, we also have useful gadgets. So let's disassemble useful function. We have our print file call. So this address is obviously going to be of use to us, and if we disassemble the useful gadgets, okay, so we have a gadget here to move the value in the EBP to the memory location pointed to by the EDI register. So this, as was mentioned in the challenge description, we're going to be looking for gadgets with move from reg to a memory address pointed to by this reg. So clearly that's our useful gadget, and we're going to need that. So let's take a note of a couple of things here. First of all, the first thing will be, well, let's take the useful gadget. So, and in fact, let's call it move gadget equals, and grab that address. And we have our print file call. So to print file, we're also going to need the address of the data section. So let's go back to, if we do read elf -s, right. Just try and mix this up as much as possible. We have in terms of tools that we're using, just to show that there's many ways to do this. We have our data address. Okay. And then so let's have a look at the ROP gadgets as well. So if we did, as before, ROPER-F for the file and input right, we can have a look at all the ROP gadgets. We have our move one already, so let's just see exactly what we grabbed. It was, we took the useful function, which you can see up here, 8048543, and that's to move the 4 bytes that are in the EBP register to the memory address pointed to by the EDI register. So the location is in the EDI register. So we have that. The issue is now that we essentially need to get the data into the EBP register in order to move it to the EDI, and we also need, in order to move it to this address, we also need to get the memory address of the data section into the EDI register so it knows where to write to. So if we search again, and this time let's search for pop and see what kind of instructions we have. So here we have one, pop EDI and pop EBP, and then return. So in this case, if we were able to get the data address onto the stack and the string, so the first 4 bytes of the string would be flag, so we would get the flag into EBP. So on our stack we have, let me try and clarify that. On our stack we have the data section address, which we pop into EDI. We have our first 4 bytes of the string, which is flag, which we pop into EBP. And then once that's done, we're able to call the write gadget. So the gadget to say move the value flag into the memory address pointed to by EDI, which is our data address, and that will write those first 4 bytes, and then we need to repeat that process essentially for the next 4 bytes. So we've got a move gadget. Let's also take our pop gadget and grab the address. And let's look at the structure of this. So the offset is going to be 44, so we're going to have 44 bytes to overflow the return pointer. And then the first thing that we're going to want to do is call the pop gadget, and this is going to pop the next 2 values. So the next 2 values are going to be the data address and then the string flag. And what we're going to do is we're going to pop the data address into the EDI, we're going to pop the flag string into the EBP, and then we're going to call the move gadget, and the move gadget is going to move the flag value in the EBP to the memory location pointed to by the EDI, which contains the start of the .data section address. And that'll be the first 4 bytes written into the data section. Obviously, we also need the .txt to be added to the end as well. So the process for doing that is going to be essentially the same. We're going to repeat the same process, except we don't need to do our offset again because we already have control of the instruction pointer. And this time we're going to do .text instead of flag. And the data address, we don't want to overwrite the flag that we just wrote. We want to do data address plus 4 because we've already written 4 bytes. And again, just do the whole same process, move that, write that to the .data section, and that should be our flag.txt is now in place in memory. So now it's just a case of calling print file with the data section address. So if you look at the challenge again, the challenge said call print file with its location as your write a string to memory, and then go ahead and call print file with the location of that string as your only argument. We also would need a return pointer here, which can just be anything. Just need 4 bytes to write in there. So this is going to be the structure of the payload, and I'm just going to go ahead and jump straight into the pwntools debug script and talk through the code on how to kind of do this manually before we look at an auto pwn script. So let's close a couple of these windows down. And if we open up Codium and the pwntools debug script, I changed this script slightly. Normally we use this to automatically find the EIP, and I've just created a separate function to find the EIP first, or it'll find the EIP without clogging up some of this code with finding the EIP, which has basically been the same code from challenge to challenge. So we start the application. We plug in our addresses here. Let's return to the notes that we put up here. So we have our data section address, which is this one that we grabbed. We have our pop EDI, pop EBP address, so that was this gadget, and we have our move, which was this gadget, and we have our print file, which is this address D0. So just making sure that all our addresses lined up correctly, and these addresses are the addresses that I've taken from GDB or Radar or wherever. We print out those addresses just for visualization purpose. Here we're actually grabbing the offset, so this function here just takes in the size of the pattern that you want to give it and the program, and then it will find the EIP offset. And then we want to build the payload. So the building the payload is just like we've done here. We have ASM NOP, so 44 no operation instructions. We call our pop gadget, and this pop gadget is popping this value into the we want to pop the location into the EDI, so this data section address, and then we want to pop the flag string into the EBP, and then here we're moving the flag string from the EBP into the memory location pointed to by this data section address, which we've just stored in the EDI. Hopefully that makes sense. Again, we're just doing the exact same thing again here, except we're doing it for .txt now, and we need the extra 4 bytes since we wrote flag already. And then finally, we call print file. We have a return pointer to make sure this works, and we give it the data section address where we've written flag.txt to. And then it just sends this payload off, and in response we should get our flags. So let's run Python pwntools debug. And you can see here that's run, it's printed out all our addresses, of the gadgets and the functions and things like that, and then it's located our EIP offset, and then finally it's printed out the flag. It had mentioned on the site doing a helper function to automate some of this. So what we could do here is, like I've created a function here to find the EIP, we could create a function to write to memory, and we could have the function say take in a string that we want to write. So it could be, you know, a longer string than this. It could be, let's say, 100 characters. We pass in a memory location, and then it would essentially just run through a looping through, doing this for each 4 bytes until it's written however many characters. Obviously, we would need to make sure that, you know, there's room for the string, but if we were trying to write something longer than flag.txt, then this code would quickly mount up, and there's no point in reusing the same code segments over and over again. I'm not going to do that here because, to be honest, if we were actually doing this, if I was doing this in a real scenario, we wouldn't do a lot of this stuff manually anyway. We would use some functions that pwntools already has to speed things up, and that's what we'll look at next. So we'll close this down and take a look at the we'll also close this and take a look at the autopwn script. So if we open up the script here, autopwn, and as in the previous examples here, we're not getting the offset, we're just putting this offset manually. It would be easy enough just to copy over that helper function that we created to find the EIP, but just to reduce on the amount of code here, and because it's so easy to find the offset quickly in GDB, I've just put that in manually. And here we create a ROP object so we can access the gadgets here. So rather than us manually finding the address of the gadgets we need, and rather than us manually finding the data section address, we can find that here. So we can just grab the data start, and this will give us the data section address. We find the ROP gadget that we need, which is pop EDI, pop EBP, and then return. I did try to do this with the move function, but let me just demonstrate here. If I do print ROP.gadgets, so it only actually prints out here 10 cached gadgets. You see here, loaded 10 cached gadgets, and there are no move instructions in here. Whereas if you do ROPER-F and write, we obviously get a lot more. And if we search for move, search dash was it? If we search for move, you can see that there are plenty of gadgets here. So I had a look at the pwntools documentation. It turns out that it hides non-trivial gadgets, and they actually suggest just using ROPER or ROP gadget if you know you want to find all the gadgets. So in this case, I didn't need to do that because the useful gadget has been stored at the function called useful gadgets. So I was able to just grab this from the elf symbols. But it's just something worth bearing in mind anyway. So just to run that again, it's grabbing our data section address, which as you can see is the same as we've used previously. It's grabbed our pop gadget and it's grabbed our move gadget. The next thing then is doing our ROP chain. So here we have done ROP.raw, so it just allows us to pass in raw parameters. You can see kind of the description here, and just as before, we're doing the first 4 bytes flag, and we're popping the data section address and the flag into the EDI and EBP registers respectively, and then we're calling this to move the value that we've just put into the EBP into the location pointed to by move EDI. And then we do exactly the same for the second to add .txt, except obviously we change the text and we make sure we deal with this offset. Finally, we call print file and just pass in the address of the string that we wrote, which is in the data section. So note that we didn't even need to find the function address of print file using this ROP. We can just call this all together, and that creates our ROP chain. Let's have a look at that. So there's our ROP chain in raw bytes. Let's also have a look at the ROP dump. Okay, don't know how to dump. So for whatever reason it doesn't know how to dump that. Let's not worry about that too much. Let's just build the payload and try and submit this. So the payload, building the payload is very simple. We have our offset, which we put in manually, but we could have automatically calculated, and we're just sending this ROP chain in it. We're just placing the ROP chain at that offset. Write the payload to the file in case we want to just replay the attack later. And let's try this out. Okay, so you can see there was a ROP chain. We sent that ROP chain and we got the flag back. If we run right with that payload, then we can see that also prints out the flag for us. Okay, so that's been the demonstration of the write challenge 32-bit. Let's take a look at the 64-bit. Okay, let's close some of this stuff down. So we're going to aim to do as much of the 64-bit analysis as possible within pwndbg. So let's open up GDB-pwndbg and the file. This is going to be quite similar to the 32-bit, but there will be some differences in terms of the registers that will be used, and obviously the size of the addresses and the data that we can actually write. So let's first of all, I just want to show in pwndbg, if you run, if you type pwndbg, you get a list of functions that we can call here. So we can make calls to things like ROPER, ROP gadget, and ROP in here. We can save the IDA database. A lot of useful functions that we can access. Let's have a look at the ROPER. So if we just type ROPER, it's listed the gadgets there. We can also do ROP or ROP gadgets. The ROPER obviously had a nice colourful output. If we do ROPER -- and then we can enter parameters, so search, let's say move. Okay, so it's a nice way to get hold of ROP gadgets. Let's take a look at the function, our useful function. We have useful gadgets as well, so the useful function is the same as last time. It calls print file, and then we have our useful gadgets. So you see this time we can see which registers we need to use essentially. So last time we used the EDI and the EBP, so we had our EDI here and we had our EBP here. So we're just using different registers, R14 and R15. We can have a look at the data section again. So if we do info target, we can get a list of the addresses here, and here we have our .data section, so we can grab this address. So let's take a note of some of these addresses. And try and gather what we need as we did the last time. So we have our data section, equals, and we have our gadgets. So we could use ROPER, or we can use the disassemble the useful gadgets. We can grab either address. So that will be our move gadget. We need a pop gadget. So before we move as we had last time, before we would move the value that's in the EBP to the memory location pointed to by the EDI, we needed to pop those two values off the stack, which was the string flag and the memory, the address pointing to the data section. This time obviously it's R14 and R15, so if we do ROPER and let's search for pop, okay, and we have pop R14, pop R15 and return. So let's grab that. This is our pop R14, R15. You'll see why I'm naming that separately. And then we have our print file, so we can disassemble the useful function. And let's just grab this address. Print file. And then finally, before we call print file, we're going to need to put the address of the location, the data section location, where the flag.txt string is stored, into the RDI register. So previously we just added it to the stack because of the way the 32-bit program will work. It'll just check the stack for the parameter. In this case, we need to pop that value off the stack into the RDI. So let's, again, well, we just search for that. So we have an address here, pop RDI, and then return. That's perfect. And that'll be called, that will be called here. So let's do pop RDI equals. Okay, so we have a list of our addresses there. We could manually in here do a cyclic pattern. Let's say cyclic 100, and if we run the application, paste it in, crash it, and we can have a look. We could take this value here and do cyclic-L. Oh, I never spell cyclic right. Okay, still can't spell it right. And there we go. So it's 36 bytes to the start of this, so it'd be 40 bytes to our RIP. You could, if we have a look, actually, what's the offset of this? .40. So we could just use the start of the RSP here for the offset. Either way, I'm just used to doing it from the RBP, but either or is fine. So we have the offset. For our first script, we're not going to worry too much about that anyway, so we're going to go and have a look at the pwndbg script and just see how we plug these values in to automate the exploitation. So let's open up the debug script. So if we compare this to the details that we have in here, again, like the last example, we have a find EIP. I've not renamed that function, but I have changed the code in the function a little bit to deal with the 64-bit. You could create two separate functions here rather than going through and doing this each time, but we're just really using the script for demonstration. It's the auto-pwn script that would be more of what I would use as a solution. So we've put in the data section address here. You can see that's the same address that we found in pwndbg. We have our pop R14, pop R15, which is here, and then we have our move gadget, which is ending 28, so that looks right. We have our pop RDI ending 93, looks good, and then we have print file ending 20, also looks good. So again, this is the same as last time, just the difference is we're dealing with the R14 and R15 registers instead of the EDI or ESI and EBP that we used in the 32-bit edition. If we look down here, we're just printing out those addresses, not really needed because we've just typed them in, but just for the visual aspect. And we find our offset first of all, which we know is going to be 40 anyway, and then we build the payload. So the difference here is last time whenever we built the payload, we had to do two separate blocks of identical code here, the first being for flag and then the second being for .txt. So you'll see I've put in a comment here that we were able to just do this in one go because it's 64-bit and we're dealing with 8-byte registers. So we can do that all in one operation. So what's happening here, just to go through it again, we are popping when we call this, we're popping R14, R15. So first we pop this data section address into R14. Next we pop the flag.txt string into R15. And then we call the move function, which will move the 8-byte string from R15 into the memory location pointed to by R14, which was our data section address. So that's all good. We've written flag.txt to the .data section of the memory, and now we need to pop RDI. So we want to pop this next value, which is the data section address. We want to pop that into the RDI register and then call print file, which will look in the RDI register for the memory address pointing to flag.txt. Hopefully that all made sense. Let's try and run that and see what happens. So you can see that all runs smoothly. We've got our addresses here. We found our EIP or RIP at 40, and then we've successfully printed out the flag. So let's move on to the AutoPwn version and see how we could speed this up and do it in a way where we don't need to manually find all the addresses. So I'll close this down. So in this script we have manually put in the offset of 40 bytes. We create a ROP object, and similar to, or the same as the 32-bit example, we're grabbing the data section address using elf.symbols.datastart. We are finding the gadget here. Obviously we're finding a different gadget. It's pop R14, R15 for the 64-bit, and then we're not able to just find the gadget for the move function, or we're not able to find the move gadget because it hides non-trivial gadgets, but we have that present. We know that it starts at the useful gadget symbol, so we just put that address in there. And then in the last example we had two lines here to deal with each 4 bytes of the string that we wanted to write to the data section. In this case, with it being 64 bits, we're able to do this all at once. So we've just changed the gadgets that are used here to deal with R14, R15 registers and increase the length of the string, but that's the only thing that's changed. And then finally, once we have written flag.txt to the .data section, we call ROP.printFile with the data section address. So we don't need to worry about popping the value into the RDI this time, popping the data section address into the RDI, because the ROP will do all that for us. As it did whenever we did the AutoPwn on the 32-bit edition. Finally, we just generate a ROP chain, just grab the raw bytes, and then we create our payload. So we say at the offset, which is 40, we want to inject this ROP chain that we've created. So if we run that, we'll see there it's printed out the data section address, it's printed out the gadget addresses, and then the ROP chain. It sent that ROP chain off and it got back a flag. And if we run write with the payload, because we just saved the payload there to, you can see here we saved the payload to a file just for future use. If we run that, we get the flag also. Okay, so I hope you've enjoyed this video on the write challenge. Any questions as ever, leave them in the comments. Thank you.